Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will continue our discussion for orbits in central field. So this is the part 2 of our lecture series. So orbits in central fields, right? So this is our part 2 of the lecture series, right? So what we have got is that let me just digress our discussion on the orbits for a few minutes, and let us now quickly focus on the conic sections which I promised in the previous module. So we will just briefly focus on the basics of the conic sections. So we are talking about geometry of conics, right? So we are talking about ellipse, hyperbola, and so on, right? So ellipse. So the ellipse, again, the ellipse is a conic section with two semi-major axes, the minor and the major, and so this is a conic section with semi-major axis. Let's say A, and semi-minor axis B, and we have B is less than equal to A, and we have that x square by A square plus y square by B square is equal to 1, right? So this is what we have, and for this the eccentricity comes out to be E square is 1 minus B square by A square. Remember, B is less than A, B is the semi-minor axis, A is the semi-major axis, right? So we see that eccentricity E square is less than 1, and the focal points of the ellipse, the focus or the focal points are F and F prime. So let me draw an ellipse that will make more sense when we talk about these points here. So these are the two focal points, F and F prime, and let me say, so my radial distance is always with regards to a certain focal point R. Radial distance is R, and theta is the angle that the radial distance makes with the x-axis. So my x-axis is the following, and the point is here A. Well, what is this? This point is 0 comma B, and this point is A comma 0, and what have we got? We have got that the focal points F and F prime, they lie on the major axis, in this case it is along the x direction, and they have the coordinates AE plus minus comma 0, and in polar plus minus AE comma 0, and in polar coordinates with origin at F, with initial line in the positive direction, in the positive x direction, with the initial line in the positive x direction, the equation of ellipse is 1 over R, which is A by B square, 1 plus E cos theta, right? So in polar coordinates we have the equation of ellipse as following, and what have we got? I think so. So that's ellipse as far as ellipse is concerned. So let us now look at another conic, which is the hyperbola. I'm going to be quick this time. So hyperbola, let us quickly draw the diagram for hyperbola. We have, so remember, hyperbola, unlike ellipse, is an unbounded conic section. And we expect the hyperbola, the two, so these are my two asymptotes. The asymptotes of the hyperbola, and the asymptotes, they typically, they make an angle alpha, right? So the alpha, we can associate alpha with our apsidal angle. We'll see how later on. But right now we are just talking about the basic conic section here, in this case hyperbola. And the equation for hyperbola, well, I think, have we included the equation for ellipse? Yes, we have included. So the equation for hyperbola is x square by a square minus y square by b square is 1, and the angle 2 alpha between the asymptotes is given by tan alpha is b over a. Tan alpha is b over a, and in this case the eccentricity of the hyperbola e square is 1 plus b square by a square, and the eccentricity is greater than 1, right? We can see that. And the focal points, of course, the focal points f and f prime, so f prime and f, this case, they again lie on x-axis, which is plus minus ae comma 0, and with the origin, well, these are my focal points, and my equation in the polar coordinates, I can rewrite this equation in my polar coordinates as 1 over r is a by b square, 1 plus e to the power cos theta. Remember, there are two branches here. Let me call this as branch A and B. Branch B, for both the branches, we have two different equations given by this plus and minus, right? So plus and minus gives us two branches of the hyperbola. So that is in terms of hyperbola. And the equation for parabola is very simple. For e equal to 1, you can put it in ellipse and you will get an equation. And that is something not of our interest for the current time. We'll mainly focus on hyperbola and ellipse, because these are the typical trajectories of these planets. Okay, so let us now come back to our discussion of the orbital motion, and let us focus on the energy and the angular momentum of these planets once again, and let us write down a concise formula for energy and the angular momentum. Okay, so we are talking about the L formula and the E formula, right? So we are talking about, well, so what have we got? So for inverse equation, for inverse square field, so again, we are going to talk only with regards to an ellipse for bounded motion, right? We don't right now talk about for the hyperbolic case. Okay, so when the path equation for inverse square field and ellipse, we are talking about bounded motion. So ellipse, the path equation comes out to be gamma by L square is a by b square, right? And this is the the Newton's law here. And what we have found here is that from here L square is gamma b square by a, and that is my L formula for the ellipse. So that is my L formula. Okay, so that is how my angular momentum depends on the major axis and the minor axis of the ellipse. where my gamma is a constant. So gamma is m naught g. M naught is mass of the sun and g is the constant of gravitation. So then suppose what we have at the point of closest approach. So at the point of closest approach, at the point of closest approach, let us say at r equal to c, the speed is v. The speed is v, and we have that energy E is given by half v square minus gamma over c. Right? At the point of closest approach, we have r is equal to c and E is this quantity. And what have we got is, we see that, let us say the point of closest approach is r equal to c. So from here, using conservation of angular momentum, L is c times v, and we can substitute v here. So this is half L square by v c square minus gamma by c, and we can plug in my L formula here. We can plug in my L formula, and we see that this is also equal to gamma b square by ac square minus gamma by c. Okay, so then further we use the fact that the orbit is an ellipse. So orbit is ellipse. Right? So what does this mean is that the point of closest approach is nothing but the semi-minor axis of the ellipse. So our C is A times 1 minus E, lies on the semi-minor axis, the point of closest approach. Right? So I can plug it into this equation above, and what I see is, and also my E for the ellipse is 1 minus b square by a square. So using all this information, all this giant information, I see that my E comes out to be, after plugging in everything, my E comes out to be minus gamma by 2a. So energy of the planet traversing on the ellipse. And that is going to be the constant, another constant, and we term this as my E formula for the orbital motion. Remember, not only angular momentum and energy, both are conserved for the planetary motion. Okay, so these are on the ellipse. I can generalize my E formula for the case of ellipse as well as for the hyperbola as well as for the parabola. So let me write down the generalized E formula. So E formula. E is less than 0. So my E formula is E is minus gamma square by 2a. Well, was this gamma square or gamma? Just a minute. I think we have, this is going to be gamma. Not gamma square, but gamma. For the E formula, ellipse, E is less than 0. So this is the case of an ellipse. And for the case of parabola, E is 0. This is parabola. And for the hyperbola, E is plus gamma by 2a. Okay. So these are the three cases for the E and for the E formula. So let us look at this brief theory with an example. So let us see an example. We have an example of an asteroid deflected by the sun. Asteroid deflected by the sun. Okay. So what we have got is that we have an asteroid which approaches sun. Asteroid which approaches the sun with speed v along a line whose perpendicular distance from the sun, whose perpendicular distance from the sun is P, and we need to find the angle through which the asteroid is deflected by the sun. Okay. So again, what we are drawing here is, let us say the sun is at one point. Let us call this point as O, and we have an asteroid. Let's say asteroid is given by this point A, and it is approaching the sun, and we expect that, well, of course, the point of approach is at a distance which is perpendicular along the direction of the speed, and this perpendicular distance is P, and the speed initial is V, right? And the moment it approaches sun, it is going to get deflected by some angle. So let me call this angle, let me call this as angle as alpha, 2 alpha. Remember, if we see closely, this path that the asteroid follows is the branch of a hyperbola, right? So what do we need to find? Find the angle through which the asteroid is deflected. So we need to find this angle 2 alpha or the angle 2 alpha for the hyperbola, right? So we can use our standard E and L formula here. So my L formula, from my L formula, my L square is P square V square, and this is also equal to V. So what have we got here is, well, from L formula I got that this is equal to gamma B square by A, and this is also equal to M naught G B square by A, right? So gamma is M naught G, and so I can quickly evaluate my, so I can use this expression here, and let us keep this expression and call this as 1, right? So I'm going to find the unknowns A and B, because my eventual angle alpha depends on A and B, right? So this is my L formula. From E formula, I see that my angle is half V square. So my E formula is half V square is M naught G, this is gamma, by 2A. So that is this is for the hyperbola. So this is gamma over 2A. So half V square is the kinetic energy. So that is gamma over 2A. So from here I can find that A is M naught G by V square, and I can plug it here, and I can find that B is coming out to be P, right? So I found A and B. From here I can find my angle. So tan of alpha is B over A, and that is from the formula of our conic section. So it's B over A, and that is going to be PV square by M naught G, right? And well, there is something different here. We need to find the angle of deflection. See, angle alpha is this total angle, right? We need to find the angle through which the asteroid is deflected. So we need to find the angle beta here, right? So beta is my deflection angle, right? So what have we got? So my beta comes out to be, from the diagram, my beta comes out to be pi minus 2 alpha, right? Or my beta by 2 is pi by 2 minus alpha, or my tan beta by 2 is tan pi by 2 minus alpha, which is cot alpha. And I have already found what is tan alpha here. So all I do is, so my cot alpha is inverse of tan alpha, and that is going to be that is, well, tan alpha was b by a, so cot alpha is a over b. So that is my deflection angle, and that completes this example. Okay, so I think we have so far discussed the Kepler's first law, that is the motion of the planets are in an ellipse, and the Kepler's second law, that is the sectorial area swipe. Rate of sectorial area swipe is a constant. How about the Kepler's third law? The third law, again, I briefly recap, was that the square of the period of the planetary motion is proportional to the cube of the radius, right? So that is what we have. So period of an elliptical orbit. The period of an elliptical orbit. To see the period of an elliptical orbit, let us look at the fact that the angular momentum r square theta dot is L, and from here we find that T is 1 over L integral 0 to theta r square d theta. Right? I have integrated this angular momentum equation, and that is what we have found. Now, so this is the equation for the time taken by the planet to move along the orbit. And if you want to find the period tau will be when the time taken is for theta equal to 2 pi. That is when we have a complete revolution. So I replace theta by 2 pi, and that will give me the period of the orbit of the planet. Now I need to evaluate this integral. Notice that the area of the ellipse, which is given by half integral r square d theta from 0 to 2 pi, is nothing but pi ab, and from here I can find that I can use this integral information into this period equation to find that my period is 2a by L, which is 2 pi ab by L. 2 pi ab by L, and this is going to be 2 pi square root a cube by gamma. Right? So 2 pi square cube root a cube by gamma, and that is my period from the L formula. Okay, so I think I am ready to state the Kepler's third law. Notice that the Kepler's third law is right away evident. Right? We see that tau square here is proportional to a cube. So that third law is right away evident from this equation for the period of the Kepler's third law. Right? So once tau is known, 3 can be, typically we use this period information to find the masses of the planets and the mass of the sun. Right? So this is, we typically know what is the period. For example, the period of the earth is 365 days. Right? And from there we can calculate the mass of the earth using this period information. Right? And so on. So let us look at this period information with an example. Let us look at this formula with an example. So what am I saying? So what we have is, the example says that we have moon, our earth moon. The moon moves in a nearly circular orbit of radius 3.84 into 10 to the power 5 kilometer, with period 27.32 days. Right? and the moon of Jupiter moves in a nearly circular orbit of radius we have radius 18.83 into 10 to the power 5 kilometer, right, with period 16.69 days, and we need to find the mass of Jupiter as a multiple of the mass of Earth, right? So what have we got here is that we are given the radius information of the moon for the Earth. We are given the period of oscillation or the period of rotation. So we are given the tau Earth. We are given the radius of the moon for the Earth. We are given the radius of the Jupiter for the moon of Jupiter and the period tau of Jupiter. And we know that tau square is proportional to a cube. We can use this information, take a ratio. So tau Earth over tau Jupiter square is equal to a Earth over a Jupiter cube, and from here I can use my mass information. I can use my tau result to see that mass of Jupiter here is coming out to be 316 times the mass of Earth. Right? I just plug in all these formulas for the period and we get to this answer. So the steps in the middle are skipped here and the readers are requested to fill in the gaps. Okay, so before we wrap up this discussion of this module, let me just talk briefly about the fact that when we talk about planetary motion, we don't talk about the motion in terms of seconds, right? The time in seconds or the time in hours, or the masses in kgs or grams, because the values are so big in when we talk about the quantities in astronomy, right? Typically the value of the mass of Earth is of the order of 10 to the power 20 or 10 to the power 30 kgs, right? So we need to come up with some unit values so that we do not end up with our calculation with large numbers, right? So in astronomy, we talk about the units known as the so-called astronomical units or AU, right? So what are astronomical units here? Astronomical units. So we have the unit of mass or the mass of sun is m naught, and the unit of length or the mass of the length is typically the length of the semi-major axis of the Earth's rotation about the sun. The semi-major axis of the Earth's orbit. So these are my AU units for mass and length, and my unit of time is 1 Earth year. 1 Earth year or 365 days. And these are the units in which we are going to talk about solving the problems in problems related to gravitation. Just briefly, I want to tell you that in these astronomical units, the quantity g, the gravitational constant g, comes out to be 4 pi square, right? We can plug in all these values and we'll see that if g comes out to be 4 pi square AU units, right? So it is not any Newton or Joule and so on. So this is in the form of AU units. And finally, if we were to write the Kepler's law, the Kepler's third law in AU units, in astronomical units, we will see that this is tau square is a square by m. Because g is equal to 4 pi square, so they cancel out each other. So tau square is a square by m. So notice that all these formulas become very simple when we use astronomical units in Kepler's law. So thank you so far for listening. And in the next module, I am going to talk about the motion of the planet in slightly, slightly standard form, or more convenient or more widely used form. So thank you so far for listening. Thanks a lot.